this school. And we have a series of talks by Bychkov, now in Haifa University. And Borya will start his series of lectures, Introduction to Topological Recursion, with his first lecture, so please.
Yeah, thank you. Thank you, Leonia, for invitation. So I'm going, so the name is Introduction to Topological Recursion, and maybe I'll start with the plan of this through lectures. We'll see how it goes. So today I'm going to talk about the origin of topological recursion. Some as I mentioned, as I state the name as introduction, so some historical remarks about topological recursion, then simple Hurwitz numbers as a running example of what about I will talk in these lectures. And then formulation of topological recursion itself, and then reformulation of topological recursion in I would say more useful way for proving something. And then tomorrow, so I don't know, I'm going to talk about the Fock space formalism. And which turns out to be very useful to dealing with all correlation functions connected to the K-p-tau functions of hypergeometric type, and to prove some recursion and topological recursion statement on this stuff. For correlation functions connected to the K-p-tau functions of hypergeometric type, and third lecture of third part of this series will be about some recent advances in investigation of mixed correlation functions, MN point correlation functions, and the recursions on them recursion for them, and topological recursion for them, recursion, topological recursion, and some duality statement on these MN point functions. And this duality statements. This last part is some recent. It's a continuous project with Petya Dunin-Barkovsky. This third part. Petya Dunin-Barkovsky, Maxim Kazaryan, and Sergei Shadrin. Okay, so this is the plan, and today, so let me start with some maybe historical observation. So what is topological recursion? Is a universal recursion which first appears in the works of Rantan and Chekhov in matrix models, and maybe the first example of an enumeration problem which fits into this recursion was the problem of counting volumes of moduli space of genus G surfaces with boundaries. So some historical remarks. So if MGN of like is the moduli space of genus G surfaces with n boundaries, length L1, etc. Ln. So it's a moduli space of this SGN is a genus G surface with n boundaries of lengths this L1 Ln capitals. So SGN is a genus G surface with n boundaries L1 etc. Ln, and omega is a hyperbolic metric. And so this is this moduli space up to isometries. And so the one can consider Fenfield-Nielsen coordinates on this moduli space. So it's a coordinates is the following. So it's you can choose closed geodesics, LIs, closed geodesics, like follows. So if you have this this genus G surface, for example, I don't know, one like this, then you can choose these guys as Li smalls, the length of these guys L1, L2, L3, and also alpha i's are angles on which how you glue this surface from the from the pens which are cutting along these geodesics. So it's angles how to glue the surface. Then there is a Weil-Petersson form omega, which is and it's doesn't, so this omega doesn't depend on the way how you cut the surface, and the the volume of this moduli space is Weil-Petersson volume is the integral of this form in the appropriate power. So this volume is an integral, was like so, and yes, this omega regime minus 3 plus n. So it's a Weil-Petersson volume. So Mirzakhani obtained the recursion on these volumes, and this recursion was very similar to some recursion which appears in the works of Ian Arlington and matrix models, as I understood. And they later proved that it coincides, and then and then people started to realize that in this recursion, which named after, which calls like CO recursion, or nowadays just topological recursion, fits very many other problems from chromobitten invariants and many others. So yes, it like some historical introduction about the appearing of this topological recursion. Maybe Lenya can say like said that I'm wrong, but as I understood, yeah, it was like follows. Yeah, now I switch to Hurwitz numbers, to simple Hurwitz numbers. I want to like also doing some intro to Hurwitz numbers, like for just to you for understanding what we count and how you can think about it. So Hurwitz numbers, simple Hurwitz numbers. So yeah, simple Hurwitz numbers is just a number of ways to present the permutation of cyclic type mu into the product of some fixed number of transpositions if we are talking about simple Hurwitz numbers. So hg mu is the number of ways to present permutation. So I'll give a formal definition like in 2 minutes. It's not very formal. A number of ways to present a permutation of cyclic type mu. Into the product of M transposition where you see I use here G and mu and no M small, but M small and G are connected with by a Riemann-Hurwitz formula. So M is equal to 2G minus 2 plus D plus N, where D is the number of permuting elements. Is the number of permuting elements. So we leave in as D. And N is the number of parts in the partition mu. So N is a number of parts in the partition mu. and G somehow is a genus of the covering. So in fact, so mu, let me say that like D is equal to mu1 plus etc. plus mu n, and mu is a partition of D. So these decompositions of a permutation are in one-to-one correspondence with the ramified coverings of the sphere, with where these transpositions form the monodromy group of this covering, and so the G is their genus of the upper surface of the pre-image, of the surface. So this decompositions in one-to-one correspondence with the ramified coverings. Ramified coverings of the sphere by surface of genus G, and these transpositions form the monodromy group of the covering. And so the picture like follows. Like we have we have a sphere here, S2, and we have like endpoints here of simple ramification. And we have one point of ramification of cyclic type mu. So we have here n preimages, and each here we have like coverings of z to the power in the power mu1, etc. mu n. So here mu1, etc. mu n. Okay, and the formal definition of this Hurwitz numbers, it's like 1 over d factorial ordered tuples of ordered transpositions. So Ti is a transposition. Where the product of all these transpositions has cyclic type mu. And you see here, I spoke only, so I didn't say anything about connectedness or disconnectedness of this upper of this surface. You don't know, you don't see of this surface. And if the surface, if we are discussing connected ramified coverings, then you should add the transitivity condition to this definition. So plus transitivity condition. which means connectedness of the surface. Say S. And yes, and it is equal to so it's equivalent to count these ramified coverings up to isomorphism. So it's so we count these coverings with the weight of 1 over automorphism group of the covering. S2, S2. So, and summation goes over all isomorphism classes of connected, if we add transitivity condition, connected coverings of degree D. So summation overall isomorphism classes of connected ramified coverings of degree D with m+1 ramification with m+1 ramification points. And where m points are simple and 1 point has primeiges mu1, etc. mu1. M points are simple. And so on this these points are fixed and ordered on the sphere, and yes, and this isomorphism, like oriented preserving homeomorphism of this upper surface S, such that you have a standard commutation diagram, simple, and 1 point as a profile mu1, etc. mu. Okay, so this is the definition, and there are so there exist ways to compute Hurwitz numbers, not without topological recursion. In my historical example, in the example of volumes of modular spaces with boundaries, as understood, again, the topological recursion is more or less most efficient way to count these volumes. For the Hurwitz numbers, there are some character formula for Hurwitz numbers, and the way to count them using representation theory of symmetric group. But topological recursion is also for Hurwitz numbers and for generalizations of Hurwitz numbers also has some very nice properties. And as a nice example of as we have a school here, as a nice example of counting Hurwitz numbers, I like to present the following example. Example of counting Hurwitz numbers. So let me count H0 d to the power 1. So we have a genus 0 covering with where this permutation has cyclic type D, so it's just a long cycle, and we are asking how many ways to, if we have transpositions, how many ways to obtain the cycle of length D, how many transpositions we have. So we have Riemann-Hurwitz formula again. Riemann-Hurwitz says that 2g minus 2 is equal to we wrote it like m is equal to g minus 2 plus d plus n. So here n is equal to 1 and g is equal to 0. So we obtain d minus 1. So it's a like minimal number of transposition which needs to obtain a cycle of length d. So we have d minus 1 transpositions from SD, and we want to produce how many ways to produce a D cycle. So it's connected with the Cayley formula. So let's take a tree with numbered vertices and edges, and tree with numbered vertices and edges. And so each transposition permute the numbers in adjacent vertices. And so if we have such a tree, we can consider like a product of these transpositions, which defined by number of vertices in the order which defined by the enumeration of edges. And so the product of transpositions we obtain transpositions. And the statement is that this so independently of enumeration of vertices and edges, if we take such a product of transposition, we obtain the cycle of length D. So independently of the enumeration of vertices and edges, we obtain in such a way we obtain a cycle of length D. And so there is a bijection between this our decomposition, which we want to count, and the trees with the vertices with numbered vertices and edges. And so what and how many trees we have? Cayley theorem. Cayley theorem says that trees with numbered vertices is there are 2 to the power 2 minus 2 trees with the vertices with numbered vertices, and there are d-1 factorial ways to enumerate d-1 edge of the tree. So finally we obtain d-1 factorials times d to the power d-2. It's the whole number of these trees. For each tree we obtain our decomposition, and in the definition of Hurwitz number we have this 1 over d factorial. So finally we obtain something like this, and it is 2 to the power, or d to the power d-3. I hope I'm right here. So yes, it's a nice example how you can count the Hurwitz numbers by hand. It's not always integers, it's rational numbers, but nevertheless. Okay, so now let me switch to topological recursion, and I will start with the usual definition of the recursion with this more or less big formula of the recursion, and then reformulate it in more understandable, I would say, maybe, and useful way. So what the initial, so it's a recursion, there are initial data for this recursion, and the initial data it's a spectral curve. It calls like spectral curve. It's some Riemann surface spectral curve. So surface with some complex structure, and with some functions of so I would say complex curve. Maybe it's better a complex curve. Sigma with some structure. From this structure, so maybe let me say the definition. So it's a complex curve with meromorphic functions x and y, with meromorphic functions x and y on it. So now I'm not saying on what are these functions are global functions, or they are just defined in some neighborhood of some points, just any functions x and y, and we from lecture to lecture I will put some or relax some conditions of this on this x and y. So today I have the following conditions. So if with the following conditions, and also from paper to paper and from case to case, there are a little bit different topological recursions, but the most the most simple one is the following, with the following conditions. So x. So let me choose some coordinate z on sigma. And yeah, so first x of z has simple ramification points, or maybe maybe I'll say that the form dx of that one form dx of z over x of z has simple zeros. For my annotations, it's better, and also zeros of the form dy of z are away from this from these zeros of dx over x. And so today I'm speaking about the global topological, so-called global topological recursion, and this means that z is a global coordinates on sigma, and x and y are global meromorphic functions. There are also a version of local version of topological recursion where this x and y functions, as I said, could be some germs and some could be defined in some neighborhoods. And this local topological recursion also very useful, for example, in the connection of all the stuff to the intersection theorem on the model spaces of curves. So okay, and what is, so we have as initial spectral curve is the following data. The like first is a spectral curve, and second from these functions x and y, and from these forms dx over x and y, you could construct the first members of the recursion, W01 and W02. Omega 01, it's of z is y of z. And omega 02. So and here this omega 02, in fact, it needs some regularization because of because of I'll plus maybe some regularization. Which I'll discuss a bit later. Some regularization.
Number 2 is a form not on the curve and it's square.
Sorry, say it again.
Omega 02 is a form not on the curve but on the square, or it's not a form.
Yeah. It's it's a two form on the Cartesian product of sigma on the sigma square.
So it's Z1 wedge to Z2.
So no, not wedge. Form one. Like a Cartesian product. Yes, and so thank you for the question, because of I should say what guides this recursion works. So it produces these forms, as you see, omega GNs, and who are these omega GNs. So let me come back to the example. So recursion. Topological recursion. Produces n forms omega GN on the Cartesian product sigma to the power n of our spectral curve. And who is this omega GN? So in the case of simple Goertz numbers, let me collect Goertz numbers into the generating series like follows. So HGN is equal to sum overall partitions of n HG mu x1 mu1 xn to power mu n, and then omega GN is equal to like just d1 etc dn HGN, so where di is just a d over dx. So it's like product of mils. So it's like a usual differentiation. And this omega GNs
Probably just dxi. Yes, it's not a form.
It's just a notation.
Where is the form? Where is the form? HGN is a function.
I mean it's yeah you're the no, yeah, I mean we obtain like follows: mu1 x mu1 and x1. So it's like a formal differentiation, yeah, on over each coordinate. And this, yeah, and these omega GNs are produced by topological recursion, starting with the first tooth, and for in the case of simple Hurwitz numbers, we have here this we have sigma just CP1, and x of z is z e to the minus z, and y of z just z. And yes, so we have here that dx over x equal to something like 1 minus z over z dz. And so it has a 1 0 in the point z equal to 1, a simple 1 simple 0. So and dy, the zeros of dy away from this point is equal to 1. Yes, and so the recursion produces, so, and you see here these forms, these n forms omegas depends on coordinate, on this coordinate z on each copy of this on this CP1, and the recursion gives you this form omega gen in the coordinate z, and then you should re-expand it in the x coordinate. So maybe let me write it. So so TR gives WGN of GN of Z1, etc. Z10 as a, so in fact it's a rational form, so it's a rational form in this z coordinate, and it has only poles only in this zeros of dx over x, but I'll state it later and write down. Now what is interesting, that so we have this omega gen of z coordinate, and then you have to, and then you re-expand it, and one can re-expand it in x coordinate. In the point in the origin, and as a Taylor coefficient obtain Hurwitz numbers.
Yeah, is it right that x is not assumed to be meromorphic? It's not in your example.
Yeah.
But dx over x is assumed to be meromorphic.
Yeah.
So x is, so to say, the logarithm of x is meromorphic.
Yeah. So x, as I said, x, yeah, x can be like any. In principle, it can be any formal series, and we're not discussing some, yeah, the x, but we're interested in this dx over x in this case, and obviously tomorrow and after tomorrow also.
Bore, it's interesting. Can we derive this result just from your previous formula for the longest cycle?
You mean So you mean from topological recursion?
Yes, topological recursion from that formula. No?
Topological recursion from
Because
zero. So let's think about zero part, yes, of topological recursion. So general
Because
zero part.
Because basically that's what we might expect. We have so we need to consider genus zero is the highest term in topological recursion, right? That's what we. Well,
So,
maybe you
I mean,
think immediately, yes, but maybe it's
I mean, so if you're so I could say the following. So if you're so I don't know. I mean, of course, this topological. So of course we can. It will works, of course, for this example. But how we derive some statements about the. So I don't know. I'm not sure.
okay.
So yeah, okay. So as a Taylor coefficient, we obtain h our h g mu. Okay, and but how this recursion looks like itself, I should say. I think for now, for example, yeah, it's okay. So the recursion, the equation of the recursion, it's like follows: omega g n plus 1, say z0 z n is equal to, so here n means tuple, so one, so let me say z n means z1, etc. z n, and like z I is the tuple of variables with indices in the set I. And also let me maybe denote by pi these zeros of dx over x. The zeros, simple zeros, p1, etc. pn. Yes. And so here I have a sum from I to in I from 1 to n, residues in these points pi's of the following huge form. It's of over omega 0,1 of sigma y of, I will say in a minute what is sigma, so minus times times the recursion. Omega sigma y of omega z n plus okay, bracket plus sum overall decomposition of G and decomposition of N omega G1 modulo, sorry. Yeah, it's okay. Modulo I plus 1 omega Z E1 times omega Z E2. And the okay, I should close the bracket. Yeah, so and what is sigma? Sigma is a deck transformation near the, so we have simple ramification points of the simple ramification point of the function x, simple zeros of, in my annotations of one form dx over x, and if we're thinking of x of z, in fact, for example, thinking, you may think of it as follows in this example of Hurwitz numbers, of simple Hurwitz numbers. This also function x itself has a simple zero in point 1, and if you are thinking of this x of z as a itself as a ramification, as a ramified covering, so I have two leaves of this meromorphic function near this ramification point z is equal to 1, and this sigma is a deck transformation, is a holomorphic, is involution, which permute these leaves of this meromorphic function. So sigma I is a deck transformation involution which permutes the leaves of the function x near in the neighborhood of the so in the case of simple Hurwitz numbers, again, we have here only one summed in this sum, and I think I so 1 or 2 more minutes and I will stop. So you see here this huge formula and this strange residue, but I'll try to hope I'll explain something tomorrow. What's written here, just prime here means in this summation, also prime here means that we exclude cases when both G is equal to 0 and N is empty. So I1 and I2 or I2 are empty. And so this huge formula means that so in the brackets, it's a recursion part, and this formulas means that you see inside the bracket we have here like n plus 2 forms, so forms on the and sigma to the power n plus 2 forms, and here this integral here is just one form, and here also we have one form. So, oops. In the end, we have a n plus 1 form, and when we take a residue in the point in these points, we obtain this n plus 1 form from the left hand side. So it's more or less okay with these, and you see here this this deck transformation uses very much here in the numerator and denominator, and here also. So it means that you may start to think about all this stuff as some like odd form due to this involution, because of even part disappears. And okay, so maybe I should stop here by now, and tomorrow we'll continue this with. So I will end the formulation of topological recursion and continue to reformulate it, and so on. Yeah.
Okay, Bore, thank you. Questions?
Question. Omega G0 do not exist, are they? And it cannot be 0 here.
So yeah. It's n is greater than 0.
And omega 1,1. Can you obtain it from this formula? I don't see.
Yes, but when during the obtaining this omega 1,1, you should use this regularization, which I mentioned here, because of otherwise you obtain some pools on the diagonal which are not allowed. So omega 1,1 is also an exceptional
omega
case.
1,1. I don't see it's G. So no terms are here applicable. G is 1. So it's omega 0. Omega 0,2. Yeah, that's going to be omega 0,2, or and to avoid the poles.
Yeah. It's okay, but the problem is that this
omega
this
0,2. Omega 0,2 has pole on the diagonal, but you substitute in one argument z, and another argument you substitute sigma of z. And this omega 0,2 of z, sigma of z, has no poles on diagonal. It extends to the diagonal perfectly.
Now understood.
So,
in
this form, the formula is applicable. Yeah.
Yeah. Oh, yeah, you're right. Yeah.
Okay. More questions? Okay, so if no more questions, so let's thanks Bore again.